A nuclear-powered ship can cross the world's oceans for decades without refueling. The heat that drives it comes from uranium atoms splitting deep inside the hull, yet the steam that turns its turbines never becomes radioactive. Thousands of sailors live and work aboard these ships every day, often receiving less radiation exposure than they would in many cities on land. We're going to move slowly through how this works, starting at the heart of the ship, where the heat is made. 1. The heart of invisible fire. A nuclear surface ship carries no fuel in the traditional sense. There are no massive tanks of oil sloshing in its belly. Instead, somewhere deep inside the vessel, protected by layers of steel and shielding, sits a core no larger than a car. Inside that core, uranium atoms are splitting apart, and in that splitting, they release heat. Staggering, relentless heat. This heat does exactly what coal or oil would do. It boils water. The water becomes steam. The steam spins turbines. The turbines turn shafts. The shafts turn propellers. And the ship moves forward. What's breathtaking is not that the process is extraordinary, but that it's so fundamentally similar to ships that came before. We took the most advanced physics humanity had ever discovered and used it to do something beautifully simple: make water hot. What makes this so captivating is that you could run this ship for 20 years without adding fuel. 20 years of crossing oceans, of powering systems, of generating electricity, all from a core smaller than most cars. The energy density is almost unimaginable compared to chemical fuel. 2. The first dream, a captain's vision. In the 1950s, a U.S. Navy captain named Hyman Rickover had a vision that seemed impossible. He wanted to put a nuclear reactor on a ship. Not just any ship. He wanted it on a submarine first, then on surface vessels. People thought he was reckless. Reactors were enormous, temperamental things kept in secured facilities on land. The idea of putting one on a moving platform that could be hit, could sink, could roll in storms, seemed like madness. But Rickover understood something profound. He understood that the ocean is vast and the world is large, and that the nation that could cross those distances without stopping for fuel would have an advantage that changed everything. He wasn't just building ships, he was building reach. He was building presence. He was building the ability to be anywhere for as long as necessary. The remarkable part is how fully he succeeded. The nuclear submarine USS Nautilus launched in 1954, and within years the technology moved to surface ships. Rickover's obsessive attention to safety, training, and procedure created a culture that has operated nuclear reactors at sea for around 7 decades without a single reactor meltdown on an American naval vessel. 3. Endless speed across the ocean. A nuclear-powered aircraft carrier can sprint at over 30 knots for days without slowing. It can maintain that pace across an entire ocean. A conventionally powered carrier must conserve fuel, must slow down, must plan its movements around the location of supply ships. Nuclear power removes that constraint entirely. Imagine you're running a marathon, but you never get tired. Your competitors must pace themselves, must conserve energy, must plan when to push and when to rest. You just run at full speed from start to finish. That's what nuclear propulsion gives a surface warship. Not just endurance, but endurance at maximum capability. 4. The reactor itself, controlled fury. Inside the reactor core, uranium fuel assemblies stand in carefully arranged patterns. Each fuel rod contains uranium that has been enriched, meaning the percentage of uranium-235, the isotope that splits easily, has been increased. In nature, uranium is mostly uranium-238, In a naval reactor, the uranium-235 content might be 20% or much higher, depending on the design. When a neutron hits a uranium-235 nucleus, the nucleus absorbs it and becomes unstable. It splits into two smaller atoms, and in that split, it releases energy, more neutrons, and radiation. Those new neutrons can hit other uranium atoms, causing more splits. This is a chain reaction. Left uncontrolled, it would accelerate catastrophically. Controlled, it produces steady, immense heat. What makes this remarkable is the precision required. The reactor must run hot enough to efficiently produce steam, but cool enough to not damage its own components. It must sustain the chain reaction without letting it spiral out of control. It must do this while the entire vessel pitches and rolls in ocean swells, while subjected to the vibrations of machinery, while operating in conditions that would destroy most industrial equipment. 5. Control rods, the hand on the throttle. To control the reaction, engineers insert control rods made of materials that absorb neutrons, often boron or cadmium compounds. When the rods are fully inserted into the reactor core, they absorb so many neutrons that the chain reaction cannot sustain itself. The reactor shuts down. When the rods are partially withdrawn, fewer neutrons are absorbed and the reaction intensifies. Withdraw them further and the reactor runs hotter. This is how you throttle a nuclear reactor. There is no ignition, no combustion, no flames. There is only geometry. The position of rods in space, the density of atoms, the probability that a neutron traveling through the core will strike a target or pass through empty space. You are controlling power output by controlling geometry at the atomic scale. The striking thing here is how analog this feels despite the extraordinary physics. A sailor moves a control rod mechanism and the reactor responds. Cause and effect, action and reaction, as tangible as adjusting a valve on a steam engine. Humanity has taken quantum mechanics and made it obey simple mechanical principles. 6. The water's journey, primary and secondary. The reactor doesn't directly boil the water that spins the turbines. That would be too dangerous. If that water leaked, it would be radioactive. Instead, naval reactors typically use a two-loop system. The primary loop runs through the reactor core itself. Water is pumped through channels in the core, where it absorbs tremendous heat from the splitting atoms. This water is kept under such high pressure that it cannot boil, even at temperatures well above 300 degrees Celsius. This superheated primary water then flows through a heat exchanger called a steam generator. There, it passes through thousands of tubes, transferring its heat to a secondary loop of water on the other side of the tubes. This secondary water is at lower pressure, so it boils, becoming steam. That steam is what spins the turbines. It never touched the reactor, never became radioactive. What makes this feel almost impossible is that you've isolated the danger. The radioactive primary loop is sealed, pressurized, contained. The steam that does the work is clean. You've created a barrier between the astonishing and the ordinary, between the atomic and the mechanical. And that barrier is nothing more than metal tubes and carefully maintained pressure. 7. The shield, layers of protection. Around the reactor core sits shielding, thick layers of steel, lead, concrete, or combinations thereof. Neutrons and gamma rays stream out from the splitting atoms, and these must be stopped before they can harm the crew or damage equipment. The shielding absorbs this radiation, converting it to heat, which is itself carried away by cooling systems. The reactor compartment is often the most protected space on the ship. It sits low in the hull, surrounded by other compartments that serve as additional buffers. The machinery around it is arranged to ensure that even if the ship is hit, even if it floods, even if systems fail, the reactor stays contained and cooled. The fascinating part is that you can be on a nuclear-powered ship and receive less radiation exposure than you would living in certain high-altitude cities or working in some stone buildings. The background radiation from space, from the ground, from the materials around you in daily life can exceed what a well-shielded reactor exposes you to at normal operations. The shield works. 8. The aircraft carrier, a floating city. The most visible nuclear surface ships are American aircraft carriers. These vessels are staggering in scale. The USS Gerald R. Ford displaces over 100,000 tons fully loaded. Its flight deck covers 4.5 acres. It carries about 75 aircraft and over 5,000 personnel. It is a city that moves. This ship has 2 nuclear reactors. Together, they produce enough power not just for propulsion, but for everything else. Launching aircraft, running radar and communications, powering weapon systems, operating kitchens, air conditioning, desalination plants that turn seawater into drinking water. The ship makes its own water. It makes its own electricity. It is entirely self-sufficient except for food and aircraft fuel. What's jaw-dropping is that this floating city can cross an ocean at 30 knots, station itself off a foreign coast, and launch aircraft every 30 seconds for weeks without stopping, without refueling. The nuclear reactors hum in the depths, splitting atoms, making steam, and that steam gives the ship a reach and endurance that no conventional power plant could match. 9. The steam catapult's appetite. On a carrier flight deck, aircraft don't just take off down a runway. They're too heavy and the deck is too short. Instead, they're attached to a steam catapult, a massive piston system that uses high-pressure steam to accelerate a 30-ton aircraft from 0 to 165 miles per hour in 2 seconds. The force is staggering, the violence is controlled, and the aircraft flies. Each launch consumes enormous amounts of steam. 4 catapults firing repeatedly during flight operations drain steam faster than almost any other system on the ship. The nuclear reactors must produce enough steam to power propulsion, ship systems, and still have surplus for launching aircraft. This is why nuclear power matters so much. A conventional carrier would struggle to maintain this tempo. What makes this remarkable is the integration. The same heat that propels the ship forward is launching aircraft into the sky. The same heat that propels the ship forward powers the steam catapults on the flight deck. The same reactor that desalinates drinking water generates the high-pressure steam that accelerates 30-ton aircraft from standstill to flight speed in 2 seconds. 10. The cruiser's role, guardian of the fleet. Not just carriers use nuclear power. The U.S. Navy built nuclear-powered cruisers designed to escort the carriers and provide air defense. Ships like the USS Long Beach and the later Virginia-class cruisers carried reactors that gave them the speed and endurance to keep up with nuclear carriers without refueling. These cruisers were fast, capable of sustained speeds over 30 knots. They carried sophisticated radar and missile systems. They could sprint ahead to intercept threats or fall back to guard the carrier's flanks. The nuclear reactor made them as tireless as the carrier itself. The striking thing here is that nuclear propulsion became part of a larger system. The carrier and its escorts became a cohesive unit, all sharing the same advantage: unlimited endurance at high speed. This created a kind of tactical flexibility that conventional fleets couldn't match. The fleet moved as one, fast and far without the constant need to refuel. 11. The heat exchanger's quiet miracle. Inside the steam generator, thousands of thin tubes carry the primary coolant, the superheated radioactive water from the reactor core. Secondary water flows around these tubes. The tubes are thin enough to transfer heat efficiently, but strong enough to contain the pressure differential. A leak here would be catastrophic, mixing radioactive primary water with clean secondary water. Yet these systems run for years without failure. The welds are perfect. The quality control during manufacturing is obsessive. Each tube is tested, inspected, certified. The engineers who designed these systems knew that failure was unthinkable, so they built in layers of over-design, safety margins that seem almost excessive until you consider the stakes. The fascinating part is that this is where the danger is contained and the power is released. This is the boundary between the extraordinary and the everyday. On one side of a thin metal wall is water that has passed through the heart of a nuclear reaction. On the other side is water that will spin turbines, just like in any conventional power plant. 12. The crew, living with the atom. Sailors on nuclear surface ships live and work within a few hundred feet of an operating reactor. They sleep, eat, and perform their duties knowing that deep in the ship's belly, atoms are splitting. For most, this becomes background knowledge, unremarkable after a while. The radiation monitors show safe levels. The training emphasizes that the shielding works, that the procedures ensure safety. But there's a psychological weight to it. These sailors are part of a select group, the nuclear navy. They undergo extensive training, security clearances, psychological evaluations. They're taught how the reactors work, what the safety systems do, how to respond to casualties. They become, in a sense, custodians of this power. The remarkable part is how normalized it becomes. A young sailor might complain about the food or the heat in their berthing, the same complaints you'd hear on any ship, while standing on a vessel powered by controlled nuclear fission. The extraordinary becomes ordinary. The miraculous becomes mundane. That's humanity adapting to its own cleverness. 13. The decommissioning challenge. When a nuclear ship reaches the end of its life, it cannot simply be scrapped like a conventional vessel. The reactor compartment is radioactive. Components have been bombarded with neutrons for decades, and some have become radioactive themselves. The fuel, even if removed, leaves contamination. The U.S. Navy's process involves removing the fuel, sealing the reactor compartment, cutting it out of the ship as a single massive unit, and transporting it to a disposal site. The USS Enterprise, America's first nuclear-powered carrier, is currently undergoing this process, a multi-year, multi-billion-dollar effort to safely dismantle 8 reactor plants. What makes this remarkable is that we're dealing with the consequences of decisions made 60 years ago. The men who designed the Enterprise in the 1950s created problems that engineers today must solve. The radioactive legacy of the nuclear age doesn't fade quickly. 14. The reactor's longevity, a core's lifetime. Modern naval reactors are designed to last the life of the ship. The USS Gerald R. Ford's reactors are expected to run for 50 years without refueling. 50 years. That means a sailor who serves on the Ford at commissioning could theoretically return for its decommissioning as an elderly veteran, and the same fuel would still be in the core. This is achieved through higher enrichment and better core design. More uranium-235 means more fuel available for fission. better neutron economy means less waste. The engineers have squeezed decades of operation from a fixed amount of fuel by optimizing every aspect of the reactor's physics. The fascinating part is what this eliminates. The Ford will never need the years-long refueling overhaul that older carriers required. It will never be vulnerable during that extended maintenance period. The Navy saves billions in refueling costs over the ship's life. The reactor, sealed at construction, runs until retirement. 15. The water maker, desalination at sea. Nuclear-powered ships produce far more electricity than conventional ones. This surplus power runs desalination plants that convert seawater to fresh water, thousands of gallons per day. The crew never worries about water supplies. They have fresh water for drinking, cooking, bathing, laundry, equipment cooling. This seems mundane until you realize what it means. The ship is truly self-sufficient. It makes its own water from the ocean around it. It makes its own electricity from the reactor. The only inputs it needs are food and, for carriers, aircraft fuel and munitions. Everything else it creates. What makes this feel almost impossible is the completeness of the cycle. The reactor splits atoms, the heat makes steam. The steam spins turbines, the turbines make electricity, the electricity powers desalination. The desalination makes water, the water becomes coolant, becomes drinking water, becomes steam again. It's a closed loop of energy and matter sustained by nuclear fission. 16. The safety record, decades without disaster. The U.S. Navy has operated nuclear-powered vessels for over 70 years without a major reactor accident. No meltdowns, no core damage, no releases of significant radiation. This record is extraordinary given the number of ships, the length of service, the operational conditions, storms, combat, accidents. This safety comes from culture as much as technology. Rickover established training programs that were notoriously difficult. Reactor operators must pass extensive examinations, demonstrate deep understanding, prove they can handle emergencies. The Navy cultivated a culture where nuclear safety was paramount, where procedures were followed religiously, where anyone could stop operations if they saw a problem. The fascinating part is that this culture persisted across generations. Sailors who never met Rickover, who serve on ships designed decades after his death, still operate under the standards he established. The institutional memory is strong enough to preserve what works. 17. The propeller's force, turning power into motion. At the end of this entire chain, from splitting atoms to making steam to spinning turbines, is a propeller, or usually multiple propellers. These massive bronze or steel blades, each weighing tons, turn through the water, converting rotational energy into thrust. A carrier's propellers might be 21 feet in diameter, turning at perhaps 250 revolutions per minute at maximum speed. The tips move through the water at enormous velocities, creating turbulence, cavitation, noise. The engineering required to make a propeller that efficient, that durable, operating under such extreme conditions is substantial. What makes this feel almost impossible is the directness of it. All that extraordinary physics, all those layers of safety and complexity ultimately result in a big metal blade pushing water backward. Every revolution is paid for with uranium atoms splitting hundreds of feet away, inside layers of shielding monitored by dozens of systems operated by sailors who have trained for years, and all of it to turn a propeller. 18. The carrier's wake, where giants have passed. Behind a moving carrier, the water churns white. The propellers drive such volume that the sea itself is disrupted. The wake can be visible from space, a straight line across the ocean, marking where the ship passed. This wake is power made visible. Each turn of the propeller requires enormous energy, and all of it comes from heat, from steam, from atoms splitting deep within the hull. The visible turbulence is the ocean responding to nuclear force made mechanical. What makes this so captivating is the directness of it. You can see the power, not the reactor, not the core, not the fuel. Those are hidden. But the wake is right there. Proof that something extraordinary is happening inside that ship. Something that moves thousands of tons of steel across the sea at 30 knots, hour after hour, day after day. 19. The weapons. What these ships defend. Modern nuclear carriers carry defensive weapons, missiles, close-in weapon systems, electronic warfare equipment. But their primary armament is aircraft. Nuclear cruisers, though, carried extensive missile batteries. The Kirovs bristled with anti-ship missiles, air defense missiles, anti-submarine weapons. These weapons were why the ships needed nuclear power to keep up with carriers, to sprint, to intercept positions, to maintain station for weeks in contested waters. This demanded endurance that conventional power couldn't provide. The reactor enabled the tactics, and the tactics justified the reactor. What makes this remarkable is how the ship becomes a platform for other systems. The reactor, this extraordinary physics marvel, exists ultimately to position conventional weapons where they're needed. All that nuclear engineering serves to put steel and explosives in the right place at the right time. 20. The radiation monitoring, constant vigilance. Throughout the ship, radiation monitors continuously measure exposure levels. In the reactor compartment, in adjacent spaces, in crew living areas, on the flight deck. The data is logged, analyzed, compared against safety limits. If readings spike, alarms sound, procedures activate, investigations begin. This vigilance is how safety is maintained. You don't trust that the shielding works. You verify it constantly with instruments calibrated to detect the smallest increases in radiation. And the data, accumulated over decades, confirms what the engineers promised. The shielding works. The remarkable part is how this surveillance is invisible to most of the crew. The monitors are there, working, recording, but most sailors never think about them. The safety systems operate in the background, ensuring that life aboard a nuclear-powered ship is no more hazardous than life ashore. And so, we've journeyed through the heart of these remarkable machines. From the splitting of atoms in cores no larger than cars, to the steam that drives turbines, to the propellers that push these giants across the world's oceans. From Rickover's stubborn vision to the carriers operating today. From the physics of fission to the human crews who tend these reactors with care spanning generations. Nuclear surface ships are a testament to what humans can achieve when we push at the boundaries of the possible. They're engineering triumphs, yes. Technological marvels, certainly. But more than that, they're proof that we can take the most powerful and dangerous forces in nature and make them serve peaceful purposes, or at least make them serve. These ships connect the smallest scales of reality to the largest. Quantum mechanics in the nucleus, thermodynamics in the steam, geopolitics across oceans. It's all linked, all part of one system. One continuous flow from physics to engineering to strategy to the shape of the world itself. What makes these ships especially fascinating is how many scales of reality they connect. At the smallest level, there is quantum mechanics. governing the behavior of neutrons inside atomic nuclei. At the human scale, there are valves, welds, control rods, and crews standing watch in quiet compartments. At the largest scale, there is strategy, fleets, crossing oceans, maintaining presence, shaping events far beyond the horizon. All of it is connected. Heat becomes motion, motion becomes reach, reach becomes influence. A continuous chain stretching from the invisible world inside atoms to the visible shape of the world itself. There is also something deeply human in how ordinary this power becomes. Sailors worry about schedules, maintenance, meals, and sleep, even as they live aboard vessels powered by controlled nuclear reactions. The extraordinary fades into routine, and perhaps that is the final lesson here. Not just what we can build, but how calmly we can live with what we build. Thank you for taking this slow journey through nuclear-powered surface ships. If you found it interesting or relaxing, consider liking the video and subscribing to the channel. For now, the reactors keep humming quietly, the oceans keep moving beneath the hulls, and the night goes on. Have a good night.